extreme observable creations. They are so intellectually troublesome that well into the 1960s, many physicists felt that while black holes are a feature of the mathematics of general relativity, nature would surely find a way of avoiding creating them. Einstein himself wrote a paper in 1939 in which he concluded that black holes do not exist in physical reality. Einstein's illustrious contemporary, Arthur Eddington, put it in rather pithier terms. There should be a law of nature to prevent a star from behaving in this absurd way. Well, there isn't, and they do. We now understand that black holes are a natural and unavoidable phase in the lives of stars, a few times more massive than our Sun. And since there are millions of such stars in our galaxy, there are millions of black holes. Stars are large clumps of matter fighting gravitational collapse. In the early stage of their lives, they resist the inward pull of their own gravity by converting hydrogen into helium in their cores. This process, known as nuclear fusion, releases energy which creates a pressure that halts the collapse. Our Sun is currently in this phase, converting 600 million tons of hydrogen into helium every second. It's easy to skim over the very large numbers in astronomy, but we should pause and marvel at the terrifying difference in scale between the stars and the objects of everyday human experience. 600 million tons is the mass of a small mountain, and our Sun has been steadily burning through a mountain's worth of hydrogen every second since before the Earth formed. Not to worry, it has enough hydrogen left to continue its tussle with gravity for another 5 billion years. The Sun can do this because it is big. 1 million Earths would fit comfortably inside. It is 1.4 million kilometres in diameter. A passenger jet would have to fly for 6 months to circumnavigate it. And yet the Sun is a small star. The largest known stars are 1,000 times larger, with diameters in the region of 1 billion kilometres. Placed at the centre of our solar system, such stars would engulf Jupiter. Monsters like these will end their lives in catastrophic gravitational collapse. Gravity is a weak but inexorable force. It only attracts, and in the absence of any stronger counteracting forces, it attracts without limit. Gravity is trying to pull you through the floor towards the centre of the Earth, and it's pulling the ground in the same direction. The reason everything doesn't collapse to a central point is that matter is rigid. It's built out of particles that obey the laws of quantum physics and repel each other when they approach too closely. But the rigidity of matter is something of an illusion. We fail to perceive that the ground below us is essentially empty space. The dancing electron clouds surrounding atomic nuclei keep atoms apart and fool us into thinking that solid objects are densely packed. The reality is that the atomic nucleus occupies only a tiny fraction of the volume of an atom, and that the ground below our feet is as insubstantial as vapour. The repulsive forces inside matter are nevertheless very powerful, and they are capable of keeping you from falling through the floor and of stabilising dying stars up to twice the mass of the Sun. But there is a limit, and that limit is explored by neutron stars. A typical neutron star has a radius of just a few kilometres, and a mass around 1.5 times that of our Sun. 1 million Earths squashed into a region the size of a city. Neutron stars tend to spin very fast, emitting bright beams of radio waves that illuminate the universe like a lighthouse. The first observation of such a neutron star, known as a pulsar, was made by Jocelyn Bell Burnell and Anthony Hewish in 1967. So regular is the pulse, which sweeps over Earth every 1.3373 seconds, that Bell Burnell and Hewish christened it Little Green Men 1. The fastest pulsar yet discovered, known as PSR J174824446 AD, rotates 716 times every second. Neutron stars are extremely energetic celestial objects. On 27th of December 2004, a burst of energy hit the Earth, blinding satellites and expanding our ionosphere. The energy was released by the rearrangement of the magnetic field around a neutron star called SGR 180620, which lies 50,000 light-years from Earth, on the other side of the galaxy. In a fifth of a second, the star radiated more energy than our Sun emits in 250,000 years. The gravitational pull at the surface of a neutron star is 100 billion times that of Earth. Anything that falls onto the surface is flattened in an instant and transformed into nucleon soup. If you were to fall onto the surface of a neutron star, the particles that were once part of your voluminous atoms would be transformed into neutrons and squashed together so tightly